create a confusion matrix that Claudio mentioned in theory, that sort of stuff, you can plot it in Python. This is like the most scientific visualization library. You also have, if you like more interactive or web-based, you have Bokeh that is based on Matplotlib, and you can do some crazy interaction, you know, parallel axis coordinates. Then you can move, select data. If you want to do more exploratory data, Bokeh is like super cool. If you have to do a plot for your paper, Matplotlib is better. That's like the two aspects. You can. This is the documentation. Again, we are going to use this magic word to have the interactive inside the Jupyter notebook. We are going to import matplotlib.pyplot as PLT. This is not to call all the module the large name. And we are going to use NumPy also. So you have like basic styles for different aesthetics of your plotting. If you use ggplot, you can in Python get the same aesthetic of the plots in here, and it's like you debate other things. Sorry. So we have the plot function. We are doing some linear space with NumPy. You have to pass, the first parameter is the x-axis and the y. This is what do you want to plot? I want dots in the values with two discontinuous lines. And that function has this label. The other one is the same, I do it a quadratic, but I want x's in the dots. So you have this function lesson that lets you allocate in the best place when you're not like obstructing the graphic or anything to put all the labels in the functions. You can set the title and the axis labels. So if you run this, you're going to have the title here. This is the label that is not obstructing any of the two functions. And you have the dot blue ones is the first function we choose, and the second one, x. You can also set color and a bunch of stuff, like you can red. A bunch of changes. Yellow. This is our fixed values, but you can consume from our function and plot it directly or stuff like that. So also you have a scatter function, so if you want to plot our only dots, you can ask x and y again. This is like random values. So let's see how we can visualize images or NumPy arrays. We use the CV2 inbreed. So now we are loading RGB data. So we have 600, 1000 columns and 3 values in each channel. That's how you have to read the NumPy shape here. So if you plot it, you have these weird colors. This is the OpenCV tree that you have to flip. So when you're using InShow, you just have to tell from OpenCV that you want the channel colors changed from BGR to RGB. So any math you do with RGB channels with OpenCV, you have to remember that they have this swap. So if you pass 0, you have grayscale. So check that we are not using the OpenCV module to visualize, we are using Matplotlib. So Claudio talked about confusion matrix, do you remember? Okay, so we are going to do a small snippet so we can plot the results of our networks and see graphically how classified. So this is like a static example. This is like an NumPy array. Here we are going to have like the real results from the net in a NumPy array. This is to set the size of the labels that you want to show. This is like a nearest interpolation of the NumPy array. So if you use inshow, it's going to do this type of plots. You have the value for the true label and the predictor label. So you are always expecting that you have like a really dark diagonal. This is like the best. If you have any confusion, you have, for example, this is class 0, 1, 2, and you have here in the y-axis you have the real values of your data, and in the x-axis you have the predicted one. So you hope that you can get the most match like in the diagonals of each one. If your confusion matrix doesn't look like this and you have darker colors outside the diagonal, you have to change the model and start changing again. And this is like the amount of elements correctly classified. So this type of color bar, you get it with this one. There is a bunch of customization. You can just put like discrete colors if you don't want continuous, and just a bunch of things. Change the color map and other pretty things. So there is in the folder you have an introduction to Diano. You can the hour, I'm going to skip it. You can get into it. It's like really cool because you have you can define functions that expect I don't know, 2 matrix, but you don't have to determine the size of that matrix, and you can pass any values. And Diano works like in CPUs or GPUs or optimization, and you can say, I want to run this gradient in this GPU. You can set the context send to GPU 1, and then you can run the other function and set run in GPU 2. Or you can set to these inputs, these 2 matrix, run these 4 several functions at the same time. So it's really nice, but you have like a strange of time. But you can check it and run it. It's really cool. And in the end, you have an example of a convolution only with Diano. So just to refresh a little bit, okay, so Claudio explained a lot of theory, so I'm like free from that. Just to refresh, usually when we have our data, we have the classifier that we have the raw data, we do some cleaning, some feature extraction, and then we get to a model and iterate with the results to evaluate what parameters change or stuff like that. Till now, we can do till the cleaning data, mostly with pandas. This is like the part we're going to clean up. This would be like the classic pipeline, but for deep learning. Sorry, no, this is already. So what's the difference between neural networks and deep learning? The thing is that Claudio also said, you have two main things. You have GPUs already. We have a bunch of data that we didn't have before. And we have cloud computing, so you can rent and run in hardware that we will never get in other ways. The thing with deep learning is you have a bunch of, it's a huge family architecture of networks. The thing is that we always do this pre-processing time when we extract the feature. So I can tell my experience, I have to put landmarks in years, and I have the years and the coordinates. And I work in one coordinate. I have the I cross a vector, several vectors, and before I save the image values, the pixel values in that area. And with that information, I train it a model or something. So deep learning takes you that part from you. You have this deep learning is they are also called hierarchical nets, because the first part is the net takes raw data and and the feature extraction is automatized. So he knowing the output, he tries to calculate the best features to get the best results at the end. So you don't have to do this engineering featuring that we always do. And when you work in computer vision, that was the restraint was that you are building a program to only recognize, I don't know, a car, models of cars, or a program that makes points in the years. So here you can take the same structure or very similar, and you get the first part is the feature extraction happens, and the second part is still a classic perceptron that only choose the model on the label. So in deep learning we have like these GAN architectures that are for synthesized images, models. Is like this network has two networks training. The first one is unsupervised. She takes a bunch of examples and tries to generate similar things. So I grab a data set with, I don't know, houses, cars, and stuff like that. And I have a second network that is receiving those images and try to classify it as car or not. And if this network fails a lot, it takes to the other net telling, hey, I'm failing, this doesn't look like a car. So the other network tries to synthesize an image that is going to fit in a car classification. So it's like two networks in the same time that are like retroalimenting between them. So that's really cool. Other use is segmentation, image segmentation. They use these structures called encoder-decoder. So you first encode your features and then you take those features to the same size of the image you get. I have another example. That example, in the end, you have the papers of these examples. You have, this is a COMNET for galaxy morphology classification. This is like the COMNET that we are going to see in this class. So you have a bunch of different types of layers that we're going to see next. You have the convolution layer that is going to try to extract a bunch of features. You are going to have a pool layer that is going to reduce the amount of features that you are getting into the network. And we are going to see a dropout that is a demo for overfitting. The other one, I want to move from this topic. This is amazing. This is Dance Dance COMNET. Do you play the game where you have to press some arrows with the music? Well, these guys take raw audio and they have the choreography for that music, so they can get new audio and make a choreography alone, only with audio. And it's going to make sense, so you can dance it. It's really cool. You can try it online. and you have the model pretrained. The other one is an Ubisoft net trainer. It's for so the main character looks humanly. The moves of the mesh are like human-like. So they train it with different paths and different structures. So if you have to, you know, how do you say? Agacharse?
Duck.
Sorry?
Duck. Como pájaro.
Ah, sí? Duck. Okay. Okay. You can duck, or if you have to move from stone and stuff like that, these guys train it with polygons. They train it with the graph of the path, and they get these amazing results. Another things you can do, a segmentation network. This is like a high resolution from low resolution. That one is landmark linears. I landmark a lot of structures in general. The good thing of deep learning is that you don't need to have this huge cluster with GPUs, because all these papers you can download like a screenshot of the best time of the network. And you can import that, and you can start training from that point. So in that point, that network runs like 1 month running in a supercluster, and you have like the best weights, you have like the last values with the best training set, and you can start from that. You don't need that month running in the network. That's the most powerful thing with deep learning. So we are going to see ComNets specifically. This is the structure, the first part. This is the input. In perceptron we have like the input layer. Our layer is going to be at least 2-dimensional for ComNets. You can have 3-dimensional if you work with CT scans, or you want to work with a sequence of videos. You can have 3 dimensions. Okay. Then you have all this part is the feature extraction. And the feature extraction is like you have different abstraction layers. So the first layer is going to have like very basic features like edge, corners, texture, stuff, really simple. And that is going to feed to the next layer, and that layer is going to recognize part of an object, is going to have memory information, more local information. And then when you move up in the network, you're going to have like a high resolution or high information level. And that is the part that goes to the classic perceptron. So this part is feature extraction, and this part is the model classification or regression. One thing I didn't tell, most of in computer vision, like the top is segmentation, recognition of what class is that thing, and detection inside of the image. Regression is not so much used, but I use it a lot because I take like my coordinates, my points are continuous numbers, so I just use this type of net to do a regression. And I don't have a class of here, I have points that tell me where is the lambda. So the first thing are the convolution layers. So it's like a discrete convolution. So you're going to have this blue square. If you see, you have 1, 1, 1, 1, and the other one 0. So you're going to have this blue square is going to pass from all the matrix and saving the values. So for example, if you put this one here, you have 1, 2, 3, and 4, and this is the convol feature you save. Okay? There are different ways of slicing, of moving inside the matrix. You can say if you want the convolves to be overlapped, or you just want to do one by one by one by one. The other thing that you can do, if you don't want to lose edge information, you can use zero padding, that is like filling the image with zeros. So when you convolve, you have all the information. Depending what are you going to use, the configuration of the filter size on the body and the stripe is going to do, you can calculate the output. So if you want to do a network for segmentation, you want to preserve the size of the image because the output has to be the same size. But if you're doing a classification to say if an image is a car or not, you just want to reduce the features as much as possible. So one parameter that we have to tune is the amount of kernel. This is one kernel, but a convolve feature, if you see, it was a cube. And the cube is how many different kernels you're going to have. So you can have a bunch of these blue, and each of one is going to give you a different feature. So for example, if you want all the borders from the right, or if you want only the borders in the image up, or stuff like that. You can hard code the kernels that you want to use, or you can let the network learn which kernel is best for the classification. So if you remember the classical perceptron, you have like one weight with all the inputs. So you can calculate the parameters that you're going to have with the connection and the node. So here the parameters you are calculating, and these are these convoluted features. This is the thing that is so huge, because you're going to have, imagine that in one convolution layer you usually have like 16 filters. So that layer is going to output 16 different images, and this is only because I'm working with grayscale images. If I work with RGB, I'm going to have 16 times 3, because it applies to each channel of the image. So that's why these networks, you need so much data, because they are so huge that if your sample set is small, they're going to memorize everything. So the thing that you can do is, in image you have a bunch of information repeated. One thing that is common to use is max pooling or any pooling. So this is very similar. You have to define the size of what you're having to count on. For example, this is 2 times 2, and you're only going to save the max pixel of this neighborhood. So I changed a convolve feature, so 4 times 4 to 2 times 2. So this is a nice reduction, and I shouldn't be losing information in the process. So usually in the ComNets, the classic, you have a convolve feature, you have a max pooling, or you have several convolve layers, and then a max pooling to reduce the size of parameters that you are training. So you have several methods of regularization. This is like spinning our water in the face when the networks learn and memorize too much. This is an easy one. You can use dropout. This is only in training time. You can put a probability of disappearing. So every time the network learns, in one epoch you have a probability that the neighborhood node is not going to be there. So you enforce the network to learn with different structures. So it doesn't depend on the neighbor. If you remember the nearest example of Claudio the first day on overfitting, if you use neighbors really small, you have like, it's very used to only the neighbors and overfits a lot. This is the same. You're just saying, don't depend on your neighbors to learn this. But this is only in training. When you have your network finished, the structure of the network is the one you define. This is only in training, that's important. It's not that you are going to run your network and each time you run it is a different architecture. It's only in training. So, an important part that Claudio says on Monday was Monday. What's the problem that models have to generalize? We have to generalize. Okay. How is that? When a new example gets into the model, it should be classified correctly. If that doesn't happen, the model just memorizes all the data and give you the correct answer. But to new elements, it has to still, if you cannot predict correctly with new elements, what's the point? I mean, it's not going to work in the real world. So one thing that we have to do is split all our data. We have like in this example, I think there are 4,000 images. We have to split. Usually, you left 70-75% of your data is going to be used in training time, and you are going to have 30 or 25% of your data in testing. What does this mean? Is that this is not going to be seen by the model in training time. So this is data that is outside out of reach from the training stage. So this is data that the model never sees. So this is the point that you can test if the generalization is good or bad. So you have this 10% of validation that is used internally. This data, you can tune your parameters and say, okay, if I fix this, or if I move the learning rate, or change the optimization method, it's going to perform well. So that data can be seen in training stage. ¿Se entiende? Está medio... Voy a castellano, no sé si... Lo importante es que este 30% quede abajo del cajón, abajo de la cama. Esto no lo va a ver nadie. En ningún momento la red va a agarrar esos datos. Es mi única manera de asegurarme que cuando vengan datos nuevos no los memorizó y realmente aprendió features discriminantes y no simplemente se me memorizó toda la imagen.
Validación es para poder calcular, ¿verdad?
Recalcular.
Claro, la validación interna es la forma que tenés de plotear el learning rate y esas cosas. La red cuando entrena, cada POC hace, bueno, este error me dio en mi dato de entrenamiento y este error, ese 10%, también lo calcula sobre el validado. Entonces después puedes medir, for example, you have, this is nice one. So you have this 10% of your data in validation. And if you see that the training set is performing awesome, it's like 90%, but your validation set is dropping, it's because just memorize everything. And it's not learning. If the validation set that is supposed to not see in that ebook or in that iteration it's overfitting or sobreajuste en sharp. So these two are the curves that you have to check out when you're training your network. And when you're plotting, you are going to have like the error. You can see the error of the training set and the error of the value. And the gap between those two curves is going to give you the overfitting. If they are like really separated and you have the training error is really low but the validation is not, this is memorizing, it's overfitting. So you have to use dropout or other regularization method to calm down the network or reduce the structure. Ahora sigamos. Antes de eso, ese es el Docker. I'm not going back to the presentation. So one interesting thing that is happening, you have the boom of deep learning is taking machine learning to production. So it's like really easy to move to a company or stuff like that. But in the scientific aspect, is the most interesting part is the introspection of the network. So we have so much computation power that we can train a bunch of networks and analyze what is happening inside. So this is a nice papers that work trying to explain a little bit what is happening in each layer. And the other one that I mentioned the other day, the bottleneck, is called, I have it, Opening the Black Box of Deep Learning via Information Theory. That's a nice paper to read.
Toda esta presentación,
Si después se la paso o está en el
¿Puedo repetir el nombre del paper?
BPC, mira acá, lo tengo impreso. Opening the Black Box, salió hace como un mes, creo. Ese es el paper que ve como el gradiente después que pasan los epochs empieza a dropear features que no le interesan y sigue manteniendo el error. Y está genial porque probaron muchísimas arquitecturas distintas y todos se comportan de la misma manera. O sea, bajan a los opacos, bajan el error al principio, pero cuando llegan a esa parte de que ya están en un error que no pueden mover mucho, empiezan a dropear o features convolucionadas o lo que sea y se quedan con lo menos posible. Another technique for regularization is the one that looks in the graph early stopping. So this is a function that you can say, okay, I'm already training 100 times, and since my 20 last iterations, my error doesn't change. It doesn't change, just ended and get the screenshot of the matrix values in this stage. It's a nice way that because when you start training, you say, okay, I want to iterate 10,000 times. But you can have this function asking each time the iteration finishes, we are really getting better or just we can stop here. So that's a nice, it's computational nice because you can stop early the training and you are not just letting the network to see so many times the examples to memorize. Y después, Jan LeCun, una vaca sagrada de Deep Learning, básicamente el creador de Back Propagation o compartido, hizo un review en el 2015 en Nature que se llama Deep Learning. Y si están en ciencia aplicada, tiene un montonazo de ejemplos de para qué lo usaron y está bastante lindo cómo explicar. Y sobre todo tiene una forma muy gráfica de explicar cómo se va cambiando los espacios de feature a medida que pasan las redes. Y eso no... Hay otras... Ahora vamos a usar la hazaña. En su momento está basada en Teano. Y lo que tenía, que por lo menos en la parte de ciencias de la computación estaba muy bueno porque cada paper que venía acompañaba una microimplementación de o una capa nueva o algo por el estilo, venía con lasaña y era bastante. Pero ahora PyTorch está genial, la documentación es impresionante, la mayoría de la comunidad científica se mudó ahí. TensorFlow lo usa muchísimo más para producción, para empresas, es de Google. Tómenlo como que es una empresa la que tiene eso y si te baja el portón te lo baja. No creo, no le conviene porque quieren tener gente que se usa el TensorFlow, pero ténganlo así. Y Keras también, Keras es súper alto nivel, o sea, no vas a poder crear tu capa, no vas a poder meter ninguna función loca que quieras hacer, pero si lo único que quieres hacer es jugar con los bloquecitos de las redes que ya están implementadas, va genial. Bueno, acá está un poquitito repetido, disculpen, era de otra. So, if you remember, Claudio says that you have like a solution space when you try to find the minimum error to the output of your network. Those also are called objective functions. You can see, so if you have, you're not going to see this, it's going to tell you there is a CUDA write sandbox error or something like that. Don't worry, it's going to use the CPU. Otherwise, if you have NVIDIA drivers correctly installed and stuff like that, it's going to use automatically the GPU that finds. So these are different types to measure the error. So if you're doing some classification like categories, you can use, for example, categorical, cross entropy, or if you only have 2 classes to say earth or water, you can use a binary accuracy. If you are doing a regression with your network, probably you are going to use a square error. These are the ones that come with the lasagna. You can also implement, your network can receive any piano function created, so that's like really cool to try things. Also, you have the activation functions that Claudio mentioned. You have the basics, and the same, you can use your own if you can build a piano function. This is just listing. Also, you can see all the optimization methods that you can get, the classic ones. So how do you use this in lasagna? You can see all the layers types. We're going to use the input one, convolution in 2D, the dropout layer, that is the one that let us regularize the network, max poly layer, that is going to reduce our feature space, and the dense layer, that is like the classic hidden layer of a perceptron. That is. So if you go to the documentation, you script, you write dense layer and the question mark, you're going to see that you have a bunch of parameters that you can fill. Lasagna has these nice default values that we are going to use. So in a dense layer, you just have to say the number of units that you want. This is the perceptron basic. And you can define the activation function that you want for each of one of those nodes. So you have your convolution layer. This one we can. So you can see you can use the stride. The stride is how the kernel is going to move around all the image metric, all the input. You have the padding. This is how much zeros you want around your images. That's a nice thing. If you remember, Claudio told us about the weights of the net. So you maybe been asking, how are they initialized? So if you are going to back propagate a value, there must be something in those nodes. So usually you use a uniform distribution or there is like basic random, and then you're going to tune. That's why the network, the first time that see the example, is going to be like a really crappy network because they have like random weights and only has one time to change these weights. There is a different type of distribution. This is using low-rod uniform. One nice thing, if you enter in the lasagna documentation, you have the paper attached to that implementation. So you make sure which time of convolution is making, or if there is an optimization algorithm, which method is using. That's really nice. So in this example, I'm saying I want 32 filters, and I want it to be 2 times 2. So I'm going to have a 2 times 2 matrix going around all the input image. and I want 32 different of these kernels. So my output is going to be 32 different images with the convolution applied. Image input. So the max pooling layer is going to ask what is the neighborhood that you want me to look at. All the things you can use rectangular. It doesn't have to be a square. We are just using a square because it's easy to teach, because you don't have to check each dimension how it varies, so we do the same. And the dropout layer only has a probability. By default, I think it's 0.5, but you can put any one you want. If you put probabilities too high, you're going to have like a really starving architecture network, because it's going to be like really a few nodes because you kill them all mostly. So you have to be careful, because one thing is that you want the network to regularize, and another thing that you are like, what do you say? Como que estás desaprovechando poder, como que te queda muy básica la red. So if you kill most of your nodes, the network is going to be like really simple architecture, and you are not letting to get any interesting feature extraction, because it's like you are killing most of the nodes and it's like really simple net. So that's a thing to look at. So another things that you have, there are a bunch of layers implemented in Lasagna. I think it's very interesting the transformer layer if you're working with images. I don't have internet here, but it's like really cool because it applies affines, and if you have Google uses for, if you have an image of a street and you only want the numbers of the house, for example, applies a bunch of affines. So the only part that goes that advance in the network is the number part. So it's a nice way. It's like a projection. If you have your picture, your number is looking like this, you can apply a bunch of affines, so you can have only the number. So if you are working with things that move or are in different position or stuff like that, it's a nice layer to remove those type of variation, like scale, translation, rotation, stuff like that. It's really nice. So you have expression layers. You can pass a Tiana function with whatever you want to calculate in that layer. So that's really nice. This is the part when you can do anything with Lasagna. And another one is a standardized layer. We are going to standardize our data outside the network, but Lasagna also gives you, okay, give me your input, I move it to mean 0 variance 1, and then pass to the next layer. So that's like a pre-processing inside the network. So we have images looking like this.
Una pregunta.
Sí.
La cantidad de nodos en la red que estás planteando,
Sí.
¿se cogen automáticamente?
No, la cantidad se da.
¿O uno se le en cada capa?
Sí.
En cada capa uno tiene que proveerle el cantidad
Sí.
de nodos.
Ahora vamos a ver cómo se arman, pero también otra vaca sagrada hizo un paper de buenas prácticas, y si bien no es para seguir al pie de la letra, es un buen punto de estar para elegir ciertos parámetros.
Celia, ¿se hace feature selection en este caso o no? ¿Que seleccionás algún tipo de imagen o le das todas las convoluciones que haces?
¿Cómo?
Cuando vos agrandas el dataset.
Sí.
No,
Acá no lo estoy agrandando, lo voy a dejar así como está.
Sí, pero si yo quiero generar una imagen con imágenes porque no tenga tantas imágenes, ¿se hace algún tipo de feature selection o decir, bueno, esta característica es muy importante?
¿Para la aumentación de datos?
No, cuando vos entrenás, decís, bueno, yo en vez de entrenar con estas 10 imágenes, quiero entrenar, no sé, con 8, porque son las que dan más información. ¿Hay algo de eso o no?
No, sí aumentar la cantidad de datos. Una cosa que no sé si
podés aumentar, pero no sabes si...
Vos decís la calidad, ¿no?
Claro, si hay algo.
Algo que no sé si llegamos a ver, pero de última está en el código, algo interesante para aumentar datos es Lasaña tiene una clase que se llama batch iterator y vos podés heredar de eso. Entonces agarra un set de datos y vos podés heredar y hacer una función que los transforme, que los rote, que les cambie el contraste de las imágenes, que cambiar colores, ese tipo de cosas. Y esas transformadas se van a entrenar. Eso nunca tocó memoria, o sea, nunca me quedé en el disco. O sea, yo no voy a tener un dataset de 20 GB en mi compu, sino que a medida, mientras la GPU está entrenando la red, yo en CPU hago las transformaciones de las imágenes. Termino la transformación de la imagen, se la mando a la GPU y yo agarro el siguiente bache y puedo retocar. Eso es bastante lindo cuando no querés almacenar, porque uno trabaja con los datos reales. Es raro que quieras guardar datos artificiales. O sea, uno entiende para entrenamiento, pero después no los vas a usar. Es algo que está bastante bien. So these images you can have they are in the repo. There are, I think, 128 times 128. They are like really small, so I can get all the data sets inside of my graphic card. And I have 3 different types of sheep. I want to see an image and tell me, okay, this is a falcon million, or this is a cowwing, or it's a lambda shuttle. So that's the classification I want to see. So this is a categorical classification. I'm not going to see where is the sheep. I'm not doing detection localization, and I'm not doing a regression. I just want to see the label. Okay, this is this type of sheep. So we are going to use OpenCV to open these images and put in a CSV file. We're going to use pandas and OpenCV. So I will tell you what this is doing. So the file, the name of the file has the sheet class. So my target, my label is inside of the file name. So I'm going to take that value, and I have a folder with all the images. I'm just telling to Python to iterate inside that folder and open each image that is here in a grayscale, and then I'm going to put all the image information in one data frame column. So I'm going to have the image here, and I'm going to have the model here. If you remember, the function factorize can take a column and assign integer values 0, 1, 2, 3 for the name of the sheet. And then we can save it in a CSV file. So in this part, we are going from PNG images to NumPy array numbers. So that's the first conversion. This takes a while, I'm not going to run it, you can run it. So you're going to have, this is like the gray values of the images are in here. This is the name of the model, and this is the encode variable. So this is the one I'm going to use for the neural net. So you can check out how the file, the shape of the file. And then we're going to use this cycle down. So the thing here is, I'm taking from the CSV file that I created, and I wanted that in a NumPy array. I think Claudio mentioned it, but all these optimization methods converge to 0. So imagine if you get in with 250 value of a grayscale and you want to that converge to 0, is crazy. So the first thing you can do is normalization. So I have all the pixel values between 0 and 1. Some networks can take a very long time if you don't normalize, and other ones just give you none and say, I'm not going to optimize anything that is not in that range. So this is the part where we scale the data from 0, 1. And we have the E that is going to be the target value that you have the class. So you're going to have an NumPy array associated with a tag, a value. So the network is going to have this image correspond to this type of shape and this other to another one. If you see here, I use V stack because I'm putting each image above the other one. So this is the shape of my final array. It's a huge array with all the NumPy arrays inside, one for each image. So I'm going to say that this is an int because it's only classes 0, 1, and 2. And this is a float because I scattered between 0 and 1. If that's an int, you're going to only have 0 ones. So this is all the imports we are going to use. And I give you this one so you can run it in home or in a cluster. This is to be fast. We are going to use like a really simple network so we can train it fast. Because this one I think 20 seconds per iteration with CPU. So I'm assuming almost 1 minute and a half things in CPU. So this one you can run it after. So we are going to run this one that is like really small. So this is how you define the architecture of your network. You have your input layer that is a tensor that has one channel. If I'm going to work with RGB, I have to put a 3 here or any number of channels you want to work with. And you have the width and height of the image. That's my input here. I'm going to give the network one image at a time. Then I'm going to build a convolutional layer. The first layer is going to have a 5x5 kernel going all the image, and I want 16 of those. Then I'm going to do a max pool layer. So with a 2x2 window, I'm going to go over my combo feature and take like the max of those to reduce a little bit. And then I'm going to have the same. In convolutional neural nets, you have this, like 6 or 7 times this thing. Because each time you iterate, you have a more high-level feature extraction. So to work nicely, you just have like at least 3, 4, 5 of these basic construction of convolution, max pooling, convolution, max pooling. So till here, this is the feature extraction part of our small network. And this one is the classification part. So I'm going to have like a classic perceptor. If you put this about empty, it's going to take 0.5. And then you have the output. The output, I have only 3 units because it's class 0, 1, and 2. Each of those nodes is going to give me the probability to think that this is this machine, this type of chip, or the other one. And this is the activation function I'm going to use. So this is only the architecture of our network. Then I have to create the network and says how I want to the learning process goes. So the layers are the list that I'm defining up. The optimization method I'm going to use is nested of momentum. The learning rate I'm going to use, this is a fixed learning rate. It's like really good use to this learning rate decreases linearly. Every time you iterate over it, you just have to decrease it a little bit more. This is just a static, this is like the basic way to use it. I'm going to set what is the objective function I want to evaluate at the end of the network. and the other ones we can see it afterward. And this max epochs is the time I'm going to iterate the network. So the things that you're going to work with is you're going to change your network structure, you're going to change your learning rate, maybe change your weight initialization, and your regularization methods. These are the parameters that you're going to be looking at when you're training your model. Validating, training, validation, till you get a model that you like, and then you pass to testing. So we are going to take from scikit-learn cross-validation. This is a function that let us split the data that we have. So in X and Y we're going to have all our data, and I'm telling to do a split with the 30% of my data is going to say for testing. And a random state is a good policy to shuffle your registry, so you don't have any correlation with the order that they appear, so it's like really nice to shuffle them. And then I have to do this reshape. If you remember, the -1 is wherever you want here, but I just want a shape of 128 times 128 with one channel. That -1 is going to be the size of my registry, my dataset. So I'm going to train with 2,924 elements. So that's our images. And this is only the training part. So I should have the 30% for testing. One thing, scikit-learn also have, this is one split. You usually, when you do cross-validation, you should do several splits. Scikit-learn has stratified scaffolds, classic scaffolds, so you can iterate and do this split several times. So you can shuffle your data, and it's not just lock the first time you choose your data. You should train it and evaluate with different types. So we will use our create net, and then we can fit. And this fit is the training part. This is the vanilla way to train it. You can also do like a for and iterate each time and do things inside the epoch and then go again. We just show the vanilla because it's going to be an easy one. So it's going to give me, this is the parameters that it's calculating. This is the first time that sees all the training set. You can see the valid accuracy in the start is like really low, it's almost random. You have the training loss, that is the blue one, and you have the valid. If you remember that 10% that you save to do the validation part, this is the green one. So if you see that, for example, your accuracy is going down every time you increase your epoch, you should just cancel the training, because if it's lowering the accuracy every time you insist the sample is wrong. I don't know how many epochs. 20. Okay. So this gives you back like a snapshot of the weights in the best error, in the last error, is not the best, it's the last one. So how can we check? We can use scikit-learn metrics, all the metrics that Claudio told in Monday, precision, accuracy, F1 score, stuff like that. You already have it implemented in scikit-learn. You can get inside the documentation and again see how it calculates each thing. You don't have to blindly think that, okay, I hope that it's using the confusion matrix to do the calculation and it's not doing anything else. So here, if you look, we are using the predict function over new data. This X test, the network never see it in training time. You have this function that is like a classification record, that you have the metrics for each class and you can have an average. Also, you can get the accuracy score, that is the one inferred with the confusion matrix. So another thing we can check is the loss plot. So for example, the blue one is the training one and the orange is the validation. If this blue line goes down the orange one and for a huge amount, it's overfitting because the validation set never gets that low. So that's memorizing. So that's the first thing you can see with these graphs. This is maybe it's telling me it's very linear how it's decreasing. So maybe I can give a learning rate a little bit higher. For example, if you give high learning rates, you can see that you get stuck in like a local minima in the gradient, so you never go more down. So that's the three things you have to check. This low is similar, the high one and the good one is not linear, but it gets the lower error possible. So another thing that scikit-learn has is grid search. So you can set a space of parameters and test it, and grid search is going to give you the best performance model and which parameters use it for that. That's brute force. So you will have to have like a really small set of parameters that you want to try, because it's going to combine all the parameters you want to try with each value of the parameter. So this is the snippet for the confusion matrix. If you see you have confusion matrix from scikit-learn that calculates which of the classes was correctly or incorrectly classified. If you don't have the same amount of data for each class, you're going to see that the plot is not that it's missing one of the classes, it just doesn't have so many examples to try. So a nice way is to normalize that, so between 0 and 1, so you don't get affected for the amount of examples you have from the testing set. So this is the normalized one, and this is the example. This is telling me that I have 330 elements of the class 0 is the Falcon one, and it's telling me that 322 were correctly assigned, and he confuses with the other two ships 4 times and 4 times. 4 images were mistakenly. ¿Cómo? Bueno, que le pifió y pensó que era un lambda shuttle o pensó que era un kawin, ¿sí? Acá el que más le está pifiando es el kawin. Si bien es bajo, es el que más error tiene. O sea que se confundió con el moneda. Una cosa interesante. If you want to take your network to production, for example, you train a network that tells you if it's a cell phone, a camera, or something like that. And eBay, when you upload the photo of the product that you want to sell, tells you, this is a camera. So I already uploaded some attributes for camera selling, and he can tell you the price. Well, this type of camera, usually they sell at this amount of money or stuff like that. You don't have to train every time you want to use the network. That will be insane. So one thing you can do, you can save that in a pickle in Python. It's the way to save permanent your data. how you do that, import pickle, and you just dump the net. This dump has the structure of the network, has the last weights, has the learning, it has everything. So you can save it and then you can load it. And this loading has the best set of, not the best, the last one you checked it, so should be the best.
Esa es exclusivamente para reconocer pepinos, ¿no?
No, Pickle se llama la biblioteca que es para serializar datos. Son unos chistosos en español. Se llama así. So you have, you can print the information of the network. So this is the one in the Pickle. You can visualize. If you have graphics installed, you can see the structure of the network for documentation or stuff like that. You can check your layers. You can use predict. So you can ask the probability. So the network, how sure is the network that that element corresponds to that class? You can see the weights, the last weight. Oh. So these ones are the first convolution layer. This is the output. If you remember the filters or the blue kernels, this is the kernels that the network learned. If you remember, you have, it was 16, I think. So you have 16 different filters. This is going past through all the input data. And you have plot connectivity. This show me how that layer, what is the output of that layer. This output is each filter passed by the input. So this is what the COMNET is seeing in that point of the network. A nice tip, if you have black activities, so if one of these images activates in black, this is like, you're not going to use that because it's like annulate of the image. Usually that means like a high learning rate. If you have 1 over 64 filters, doesn't matter. But if half of your filters have black plot activities, it's like the learning rate is too high. So a nice thing we can do, we can try this over video. So this is to sort of real time, you can do some prediction with the network. You can use OpenCV as we shown. We can take each frame of the video and process it like this. So we have to normalize the data, pass it to Flow32, and reshape it for the net. So don't worry, this is only for the demo. This always happens. So you can see what thing he is with the information. I can show it again because it fails in the beginning. So I will stop here and you can start running these things in your computer and we can see errors and stuff that happens. If we have time, I have a regression network.
Celia, tengo una pregunta.
¿Por qué elegiría tanta cantidad de filtros, tanta cantidad de unidades?
Son pocos para que 5.000 sigue siendo poco para el entonces yo
O sea, acá, ¿no? Que le agregas es una interacción con la salida. Y eso es honor, familiaridad,
Y ahí podríamos hacer más. ¿No?
Y el contenido de los kernels.
Sí.
Eso.
Esos kernels son los que aprenden.
Dale.
Los kernels en el